First one, super basic. Learned this on the first day. Square root of 7 squared. We know that squaring something and square rooting something are inverse operations, therefore they undo each other. They cancel each other out. So the answer to number 1 is plain old 7. Number 2. What I recommend on number 2 is that when the radicand is a large number, like in the thousands, and you don't recognize necessarily if it's a perfect square or what perfect squares go into it, I recommend just trying it out. Put it in your calculator and just see. Maybe it really is a perfect square. And in this case, on number 2, that is a perfect square. What is it? Cool. So if you plug that in your calculator, 1,000 square root of 1,296, and it spits out a whole number at you, you don't even have to factor tree it. You don't have to do a single thing to it. You are done. I don't even require you to show work if it's a perfect square. Okay? Now, if you get an ugly decimal in your calculator, unfortunately that's a dead end, and you have to go to that radicand and you have to factor tree it, or you have to spot the perfect squares. All right? But number 2 was a perfect square. No work needed. All right, number 3. We're going to multiply the numbers on the outside separate from the numbers on the inside of the radical. 7 times 3 is 21. 2 times 24 is 48. And then we know that we are not done when our radicand still has perfect squares in it. So we need to factor tree the 48, or in other words, simplify the 48. So 48 is 16 times 3. I'm going to do it the perfect square way. 16 is a perfect square. Square root of 16 is 4. So I know that a 4 escapes and a 3 is left over. And so that's how we get 48 root 3. If you factor tree it, you'll get the same thing. A 2 will escape, and a 2 will escape for a total of 4 when you multiply them. All right? Check your homework answers. It was a short but good homework. Oh, did I switch my numbers? Awesome. Sorry. Good catch. 84. Thank you, thank you. 84, of course. 4 times 21. Thank you. The homework answers, I did a lot of these online and I already posted them. So if you look at the homework help, I did like, I don't know, 70% of these already online. So Pythagorean Theorem is in for a comeback. So we totally spent time with the Pythagorean Theorem first semester. We're going to spend more time with it this semester because we have new knowledge now. First semester, when we solved for a missing side, we took a square root of something and we just rounded the decimal answer because we didn't know what else to do with it. Now we know how to simplify our answers. So now we can simplify our radicals and our answers can be exact instead of being approximate like it was before. Just a reminder, when we're doing Pythagorean Theorem, A and B are the legs of the triangle and C is the hypotenuse. How do you know which one is the hypotenuse? If you can't tell which side is the longest, it's always the side away from the right angle, across from the right angle. You can draw an arrow from the right angle and you will be pointing to the hypotenuse. Pythagorean Theorem only works on what kind of triangles? Right, triangles. Never try to use Pythagorean Theorem on a triangle that is not right. So, this is Pythagorean Theorem radicalized. Ha ha ha. It's Pythagorean Theorem with radicals. So go ahead and solve for x like you normally would, but now you know what to do with a side length when it isn't an integer. Let's get started. A squared plus b squared equals c squared. Let's do some cleaning. 25 plus 3 equals x squared. Are we all okay with that? 28 equals x squared. Now, our goal is to find out how long the hypotenuse is. Our goal is to solve for x. So to solve for x, you need to get x all alone. Right now, x has not been solved for. It's not all alone. To get x all alone, you do the opposite of what's being done to it. Right now, x is being squared. The opposite of squaring something is square rooting. So the squared and the square root cancel. So x is the square root of 28. Now, of course, we know that that is not simplified. So we go in there and we simplify. However you want to do that. The 2's escape. The 7 is left over. And that is the final answer. X is 2 root 7. That is the exact side length. It's not a decimal approximation. It's the perfect length of the missing side. All right, go ahead and try this one. This one looks super innocent, doesn't it? This one looks really innocent. It's a 12 and a 25. You're kind of thinking the answer is going to be nice, and then you realize it really isn't. I just wanted you to see one like this, though. Be careful, 25 is the hypotenuse, so you're not writing 12 squared plus 25 squared equals x squared. No, 12 squared plus x squared equals 25 squared. What you're really doing is hypotenuse squared minus leg squared. Alrighty, so you go to your calculator, you can simplify the right. 25 squared minus 12 squared, and you get x squared equals 481. And then we know, just like last time, to solve for x, to isolate x, you square root both sides. And then something awful happens. You start to factor tree this 481, and you're like, ugh, it's not divisible by 2, it's not divisible by 3, by 4, by 5, and you're trying on your calculator, you're trying to find something that goes into 481, and what do you get? It's good. You have to work your way all the way up to 13. 481 is 13 times 37. Guess what? 13 is a prime number. Circle it. 37, try as you may, divide it by 2, 3, 4, 5, keep going. 37 is also a prime number. So what happens? Nobody escapes math jail. Everybody's stuck. Nobody found a twin. So the answer to this problem is square root 481. That's as simple as our answer can possibly get. So I wanted you to see one where the answer didn't factor tree, it didn't simplify at all. And you saw one now. So Nas was saying, if you go to your y equals, and you want to know what the factors are of a certain number, for example, that horrible number we just worked with, you go to y equals and you type the number divided by x. Then you go to your table. And your table's going to have your x's and your y's. And you're trying to find whole numbers in x and y. And when you find a whole number, those are some of the factors of x. Try this problem. So be careful. We're not going to say x squared plus 8 squared equals 10 squared because x is not the leg of a right triangle. Remember, we're only allowed to use Pythagorean Theorem on right triangles. So I'm going to call this a different letter. I'll call it a. A squared plus 8 squared equals 10 squared. Are you with me? Beautiful. I totally made up for that last one, right? Where the answer was so ugly. And yes, we are allowed to assume that both sides equal 6 because it's an isosceles triangle. Had this triangle not been isosceles, we wouldn't have been able to solve for x. X is 12 because a happened to be halfway across, half of x, only because it was isosceles. All right? Now, when you do Pythagorean Theorem and you get a whole number answer like 6, you have just found what's called a Pythagorean triple. Say it. Pythagorean triple. Pythagorean triples are really useful, and they come up a lot in nature and in math. Pythagorean triples are simply whole numbers that work in Pythagorean Theorem. Whole numbers that satisfy a squared plus b squared equals c squared. I tried to list the ones that come up most often. 3, 4, 5, because 3 squared plus 4 squared is 5 squared. 6, 8, 10, that one was from here. 6, 8, 10. 9, 12, 15. If you notice, these two are just a multiple of 3, 4, 5. Take 3, 4, 5 and double it. You get 6, 8, 10. Take 3, 4, 5 and triple it. You get 9, 12, 15. So you can create more Pythagorean triples on by taking a triple that you already know about and multiplying it by a certain factor. 5, 12, 13, I use this one a lot as well. 5 squared plus 12 squared equals 13 squared. Not even kidding. When I make lessons and I want to make sure the answer's pretty, I totally Google Pythagorean triple, and I just look for a nice pretty list. Look at this. Look at all these triples that exist. Oh my gosh. Ah. So when I want the answer to be pretty, I just go to a list. I'm like, oh, this one looks good. 24, 70, 74. And then, oh, you can't see that. But anyways, and then I use those as the side links to ensure that the answer is a whole number. So anyways, that's what a Pythagorean triple is. Let's practice using a couple triples. The beauty of Pythagorean triples is that if you memorize them, kind of like perfect squares, you don't have to solve anything. You don't have to do any math. So if you've memorized 5, 12, 13, then boom, A is 12, and you did not do any Pythagorean theorem. You didn't have to show your work. Number 2, 3, 4, 5. Because 3, 4, 5 satisfies the Pythagorean theorem. So memorize them. It's a shortcut. Don't memorize them. You'll just have to do it the long way. Find the value of x and leave in simplified radical form. So of course we're going to need a stepping stone before we find x. We can find a right here first. This one is also a Pythagorean triple. If you already know it, you can just answer with that one. But if you don't know it, you can do the math. What do we get? 144? So 12. We know since this trapezoid is isosceles, that's going to be 12 on the identical side over there. And then we need this empty space in the middle, but we can just look up and we see that that segment is 10, and therefore our final answer is 34, using the segment addition postulate. Very good. Ooh, this is a good one. We have 2 more examples left, so stick with me. 2 more examples. I'm going to give you a minute to try it without my help. All right, let's get started. A squared plus B, oops, that's a 3. B squared is equal to, I'll call it C, C squared. So we begin with a right triangle, the one that we know 2 things about. You have to know 2 things to do the Pythagorean theorem, 2 sides. And so now we know square root of 2 squared is 2, square root of 3 squared is 3, 2 plus 3 equals C squared. 5 equals C squared. We know to solve for C, we need to square root both sides. So C is equal to none other than the square root of 5. So we can go plug that in our problem. But now we need to do Pythagorean theorem on top of Pythagorean theorem. Pythagorean theorem, take 2. 2 squared plus square root of 5 squared equals our final answer squared. All right, 2 squared is 4. Square root of 5 squared is 5. This is looking good. 9 is equal to x squared. We know we square root both sides, and x is, dun, 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 3. It's technically plus or minus 3, but we throw out the negative because triangles cannot have a negative side length. Wasn't that one fun? Last one. Okay, now, I'm not going to lie to you. We're going to learn a shortcut for this next week. But I want you to know where that shortcut comes from. I want you to know how long it would be if we didn't have the shortcut. So let's solve this one the long way. Hopefully you drew a diagram. The diagonal of a square, oh, that's a typo, is 13 centimeters. Find the length of the sides of the square. How are we even going to begin? Yikes! I'm just going to start adding markings to my picture. close. Now, since it's a square, the unique thing about it is that all of the sides are the same length. So if I call one of the sides x, I'm allowed to call the other side x. All right, so if I do Pythagorean Theorem, a squared plus b squared equals c squared. What is x squared plus x squared? 2x squared equals c squared. Uh-oh. This is not looking pretty. Don't write that as a decimal. Did you hear me? Don't write that as a decimal. All right. We have x squared equals 169 over 2. How do you solve for x? Square root both sides. Cancel, cancel. X equals, well, I know that I can square root the numerator and the denominator separately. The square root of 169 is 13. Unfortunately, the square root of 2 is just the square root of 2. Is our answer final? Not yet. We have to do our favorite thing, rationalize. All right, so multiply across the top, and you get 13 root 2. Multiply across the bottom, square root 2 times square root 2 is 2. And that is the reality. That's the answer. But like I said, I'm going to show you a shortcut next week, and you're going to be like, hallelujah. All right, the lesson is over. You may start on your homework. Have a great day.